Okay, next we consider lambda square level. So at order lambda square, we want to render the theory finite at this order. So in this case, we have divergence in both 2.1 pi and 4.1 pi. For 2.1 pi, we have the following diagrams at order lambda square. I mean, up to order lambda square, we have order lambda diagrams. These are order lambda diagrams that we just discussed in the previous slide, and then order lambda square diagrams, which is this one, and then we have the setting sun diagram. And then because of this additional vertex, which is at the order lambda, we can get a diagram like this. This will be order lambda square because this is the original vertex that is order lambda, and this is a new vertex which is also order lambda. So this new Feynman diagram that we introduced at the previous stage is going to give rise to a new diagram here. For the 4-point function, 4.1 pi, I mean, if I draw 1 pi, then I don't have to ampute the legs. That calculated up to order lambda square. The first diagram is the tree diagram. Then we have three lambda square diagram at one loop. Which we calculated earlier. Now, of course, this first diagram, this diagram is given by the vertex factor lambda minus lambda mu to the power epsilon. And these three together, we had this result. This is given by this result. This one, where we have 1 over epsilon pole, and the rest is a finite term. So we should write this result here. Let me call G1 m hat square s comma t comma u, which is a finite piece, and that's given by this expression. To absorb this 1 over epsilon term, we need an additional diagram. Which should be given by a new vertex at lambda square, whose vertex factor must be negative of this factor, which is -3 lambda mu to the power epsilon lambda hat times 1 over epsilon plus a finite ambiguity, which is G1 epsilon n hat square. This is finite as epsilon goes to 0. So this is a new 4 vertex that we are introducing to absorb this one loop diagrams, one loop divergence. Also, we should keep in mind that this vertex absorb the divergence coming from this diagram, but there is no guarantee, a priori guarantee, that this diagram where this vertex was tuned to cancel this divergence, there is no guarantee that all the divergences will be cancelled here. Okay, and not only that, we shall get back to this 2-point calculation diagrams again later on. Before that, let us write down the counter term Lagrangian. So counter term Lagrangian will be given by earlier we calculated it for phi square, which is this one. So let me write this. But now you see in the Feynman diagram, in the original Lagrangian, if we go back to the original Lagrangian here. So in the original Lagrangian, we had this phi-4 interaction, which are the strength of lambda mu to the power epsilon by factorial 4. Corresponding to that, the Feynman diagram, the coupling that appears comes with a minus sign. Okay, and this new vertex also comes with a minus sign, and therefore the counter term Lagrangian will have the same term with plus sign. And we must also multiply a factorial 4, 1 over factorial 4, which is the symmetry factor for phi to the power 4. So this is 3 lambda mu to the power epsilon lambda hat 1 over epsilon plus G1 times phi to the power 4. So as a result, so we had earlier shown the expression for 2-point function, which is this finite, which I should mention this, let me call it finite. If this is the finite part after adding the counter term diagram. So in this case, we should have up to order lambda square and finite piece after cancelling with the counter term diagram. We have this tree level contribution, and then lambda mu to the power epsilon times So the finite piece will be the 1 over epsilon term cancels, and it will be this small g1 minus capital G1. Okay. Now, notice that this new vertex, it's a 4-point vertex. Earlier in the 2-point calculation, 2.1 pi, the original 4-point vertex contributed. So now this original 4-point vertex had order lambda, but now we have a 4-point vertex at order lambda square. So this must also contribute at order lambda square in this. So there will be another candidate here in this. So we should have modification to 1 pi is up to order lambda square at the original terms plus another diagram, which is this. This is also at order lambda square. So these are the new diagrams, and there is no reason to expect that here the cancellation is complete. However, if the cancellation is not complete, we should calculate this quantity completely, and then we should find out the divergence structure and then add a new counter term, which is a counter term diagram, which is of this sort, but at order lambda square. This was the counter term diagram at order lambda for the 2-point function. Here, we seem to have, in general, on general grounds, we would not expect, there is no reason to expect that that the cancellation is complete here. If it is not, we should calculate it, and if it is not, then that would introduce another 2-point function counter term diagram at order lambda square. So that is what we should do now. So let us first calculate this diagram. So what we are trying to do now is to calculate 2.1 pi at order lambda square completely. And the first term to calculate is this one. This has an original vertex, which is minus lambda mu to the power epsilon. And and the second vertex, which is this one, and that vertex factor is given by this one. So let me copy that. And then I should now calculate this loop diagram, and that should be given by the symmetry factor is half, and then ddl over 2 pi to the power d. And there are two propagators because there is one vertex here. There are two vertices, and therefore there are two propagators. So and that is 1 over L square plus m square whole square. And this integral is nothing but the standard integral that we calculated earlier, I1 d comma 2, where a is equal to 2. So what we have is half times lambda mu to the power epsilon times m square lambda hat times 1 over epsilon plus f1 epsilon n hat square times a result of I1 d comma 2, and that's given by m squared to the power d by 2 minus 2 divided by 4 pi to the power d by 2 gamma 2 minus d by 2 divided by gamma 2. Now write d equals 4 minus epsilon and write an entire expression in terms of epsilon. This will be m squared to the power minus d equals 4 minus epsilon. So this is m squared to the power minus epsilon by 2 divided by 4 pi to the power 2 minus epsilon by 2 times gamma 2 minus 2 plus epsilon by 2. This lambda and this 4 pi square can be combined to make lambda hat. So then that would be half lambda hat square times m square times 1 over epsilon plus f1. This is m square over 4 pi to the power epsilon by 2 minus epsilon by 2. So one can write m square over 4 pi mu square to the power minus epsilon by 2, where I have combined this mu to the power epsilon factor here also. This times gamma epsilon by 2, and that has an epsilon expansion which one can get from this result. Gamma epsilon by 2 will be n equal to 0 for this. Substitute n equal to 0 here, so 1 over epsilon. If it is 1 over epsilon plus psi 1, since it is epsilon by 2, it will be 2 over epsilon plus psi 1 plus order epsilon. So half m square lambda hat square 1 over epsilon plus f1. This is m hat square. So m hat square to the power minus epsilon by 2, which is e to the power minus epsilon by 2 log m hat square, and that can be expanded as 1 minus epsilon by 2 log m hat square. Of course, plus order epsilon. Order epsilon square. So we can write it as 1 over epsilon plus f1 times 2 over epsilon plus psi 1. So the maximum pole is 1 over epsilon square, because it has 1 over epsilon in 2 terms. So the 1 over epsilon square term will be 2 over epsilon square. You take this term, and 1 here. And then let me calculate 1 over epsilon term. So we take 1 over epsilon times psi 1 times 1. So that gives a psi 1. Then f1 times 2 over epsilon times 1, which gives 2 f1. And there's another source of 1 over epsilon term, which is if you multiply this one, and this one. So that will be minus log m hat square. Right? Plus order 1, which we are not calculating. So the result is that Next, we shall calculate the other diagram, this one.